Welcome to another Mathologer video. Have a look at this. First squish this square down by a factor of 2 and then stretch the resulting rectangle horizontally also by a factor of 2. Is this rectangle larger or smaller than the square we started with? Easy, right? The answer is neither. They have the same area. First squishing by a factor of 2 gives the shape of half the original area, then stretching by the same factor doubles that one half and gets us back to where we started from. Of course, the same is true for any shape and any factor. For example, take this cute cat shape and choose the factor to be 3. Then squishing by a factor of 3 followed by stretching by the same factor gives this very different looking cat monster that has exactly the same area as the cute cat we started with. Here's an interesting question for you. Do anti-shapeshifters exist? Is there a shape that is immune to these squish and stretch transformations? Immune in the sense that the shape is exactly the same before and after applying the transformation. Is there such a shape? And I don't mean trivial stuff like a point or a line. Obviously those are immune. No, a shape that actually has a non-zero area. Believe it or not, anti-shapeshifters do exist. And these anti-shapeshifters form the natural visual heart of logarithms, hyperbolic functions, the theory of special relativity, and much more. And now that I've got you hooked, I'm sure that you can't wait for me to dazzle you with all the amazing anti-shapeshifter maths that nobody ever mentions in school and university. Well, happy to oblige. Okay, so prepare for the grand entrance of the prototype anti-shapeshifter. For this, I need a Rubik's Cube and a drill. Looks familiar? Yes, that's our good old friend 1 over x. Nice grand entrance, huh? I bet you didn't know that 1 over x was hiding in a spinning cube. I also bet you didn't know that 1 over x leads a second life in anti-shapeshifter land. To see 1 over x in action in anti-shapeshifter land, let's focus on its branch in the first quadrant. I claim that this orange shape is an anti-shapeshifter, that this shape is immune to any squish and stretch transformation. Let's do a quick spot check. Let's squish and then stretch by a factor of 2. But first, let's check about the shape to also see what's going on within the shape as it transforms. Okay, squish down, okay, and stretch to the right. Very satisfying, isn't it? That our 1 over x shape stays unchanged under squish and stretch transformation, no matter what factor we use, is easy to check algebraically. Really just a one-liner. Maybe one of you year 10 students watching can do this in the comments as homework. So both the overall shape and the area of this figure stay unchanged whenever we squish and stretch. But what is the area of this shape? Well, there is a really nifty way to figure this out. Let me show you. Focus on this spike here. There, the blue spike spiking off to infinity to the right. Okay, squish and stretch by a factor of 2. Squish and stretch. As always, the new blue spike has exactly the same area as the original spike. But at the same time, the new spike is contained within the original spike. There. Curious, huh? Can you already see where this is going? Well, we can express the fact that one spike is contained in the other like this. Original blue area equals the second blue area plus the excess green area. Green plus blue equals blue. Cancel the blue on both sides and you get... we conclude that the green shape has 0 area. Of course, this is nonsense. How can we avoid this nonsense? Well, let's have another look at our equation. Now, if the blue is an ordinary number, then we can definitely cancel, and the result is nonsense. So the blue must be an extraordinary number, right? Extraordinary number? What comes to mind there? Well, yes, infinity. Right. The only way the nonsense can be avoided is if the blue spike has infinite area. Of course, this implies that the area of the entire shapeshifter is infinite too. And now one of the most iconic truths of mathematics is lurking just around the corner. And so let's quickly chase down that iconic truth before we continue with the main arc of today's story. Okay, so our spike has infinite area. Zoom in. Zoom, 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 zoom. Now have a look at this infinite staircase. What is its area? Obvious, right? Infinite too, since the staircase contains the infinite spike. On the other hand, the area of the staircase is also the sum of the areas of its infinitely many rectangular steps. And what are those areas? Also easy. Base times height. All the steps are 1 unit wide, and so their areas are equal to their heights. And what are those heights? Well, our staircase is constructed to align with 1 over x, and so the heights are 1, 1/2, 1/3, and so on. Now, as we already figured out, the areas of the steps are the same as their heights. And so this shows that the super famous infinite sum, 1 plus 1/2 plus 1/3 and so on, sums to infinity. As I said, one of the most iconic truths in mathematics. Super neat proof, don't you think? Those of you who know a little bit of calculus may have seen this proof before, but I hope you can all appreciate that what's extra super duper nifty about the way I presented this proof is that it skips all the calculus. Okay, let's continue with our main story. Let's focus on the area under the curve between 1 and some number x. Let's call this area a of x. Guess what the a stands for? Anti-shapeshifter, of course. Well, of course not. A stands for area. Okay, so this is a of 3. And this is a of 2. Now prepare yourself for something super pretty. I'm going to calculate a of 2 plus a of 3 a la shapeshifter. What does that mean? Okay, here we go. First a of 2. At x is equal to 2, our 1 over x is equal to 1/2. Move in the grain shape. We adjust the height of the green shape by squishing by a factor of 2 there, and we compensate area-wise by also stretching by 2. Now shift the green like this, a perfect fit because of the anti-shapeshifter, which shows that a of 2 plus a of 3 equals a of 6. Let's do a couple more experiments with this visual adding a la shapeshifter. First off, let's switch the order, so we begin with a of 3. So at 3, our 1 over x is equal to 1/3. Okay, squish and stretch by 3, squish, and stretch, and shift to align. And as expected, we get a of 6 again. Although we know why this works, it still looks pretty magical, doesn't it? Okay, next, a of 2 plus a of 2. Let's do this on autopilot. Stretch. A of 2 plus a of 2 is a of 4. Okay, one more, a of 3 plus a of 3 on autopilot, going down, squishing, stretching, aligning. A of 3 plus a of 3 is a of 9. Great. So what's the general rule? Can you guess? Well, pretty obvious, right? A of x plus a of y is a of x times y. Sums somehow turn into products. I leave it to the keen among you to check that this really always works. Again, very easy. And again, to make sure that you really know what is going on, please write up your proof in the comments. Anyway, sums turning into products, that sounds familiar, doesn't it? Where have you encountered something like that before? Yes, logarithms. And of course, it's exactly this so-called product formula for logarithms that made logarithms so important in the old days, since, reading from right to left, this formula allowed us to translate the painful task of multiplying two numbers into the much simpler task of adding the logarithms of the two numbers. Anyway, looks like our mystery area function may be a logarithm in disguise. And what we've done so far amounts to a very beautiful visual way to introduce logarithms. And so, is our area function a logarithm? Well, let's see. Apart from this product formula, there's also the quotient formula for logs, that one here. And it's also easy to visually see that the corresponding formula works for our area function. Looking good. What about the power formula for logs, that one there? Well, that also works for our area function. Let me just show you quickly why this works in the simple case of n is equal to 2. There, 2 times a of x equals a of x squared. Here the simple proof. 2 times a of x, that's just a of x plus a of x. But then our product formula tells us that this is equal to a of x times x. And since x times x equals x squared, we're done. That was easy, right? We can now iterate this argument to show that the power formula is true for all positive integers, 3, 4, 5, and so on. But now, challenge for the keen among you. How do you show that the power formula works for all integers, not just the positive ones? And then what about all the rational numbers and all the real numbers? Leave your thoughts in the comments. Anyway, with enough work, we convince ourselves that our area function works like a logarithm and quacks like a logarithm. so presumably it's a logarithm. But then we have a puzzle. And what's that puzzle? Well, there's not just one logarithm, there are infinitely many, each of them pinned down by their base. So if our area function is a logarithm, what is its base? Well, let me show you a super nice way of answering this question. Okay, so apart from the product, quotient and power formulas, what else do we know about logarithms? Well, there are also those special values. Well, let's see how rusty your logs are. Log of 1 is equal to what? Well, any log at 1 is equal to 0, no matter what the base is. How about a of 1? Well, that's also 0. Pretty obvious. No area, and so a of 1 is equal to 0. Great. Now, what's that other special value? Remember? Almost? Okay, I'll help you. The log to the base of b at b is always 1. Confused? Take my word for it. You once knew this. Anyway, if our area function is really a logarithm, that should give us a way to figure out what its base is, right? We simply have to figure out for which x our area function spits out the value of 1. Okay, let's first convince ourselves that there actually is such a special value. That's easy. We know that a of x is 0 when x is 1, right? Now, as we push x to infinity, there's more and more area, and so a of x gets larger and larger. In fact, because the blue spike has infinite area, we know that a of x explodes to infinity. But then, on the way from 0 to infinity, our area function must come across a value of x where a of x is equal to 1. Cool, huh? Again, it's that special value that we're hunting. Okay, we want area 1. Well, here then, for easy reference, is a unit square which has area 1. Now let's have a look at a of x for different values of x. Let's start with x is equal to 2. Is 2 our special number? Well, obviously not, since a of 2 is smaller than 1. There. The orange a of 2 fits into the unit square like this, and so the orange area is smaller than 1. This means that 2 is smaller than the special number we are looking for. Okay, so what about a of 3? There. Well, let's see. Aha, we get an overlap, and so a of 3 is too big. So what that means is that our special value is somewhere between 2 and 3. Nice visual argument, don't you think? And now comes an even prettier argument that even the jaded, know-it-all calculus demons among you will like. Guaranteed. Okay, let's step back and put x halfways between 1 and 2. There, x is equal to 1 plus 1/2. Shift the orange into the unit square. Here comes the first niftiness. Fit a second copy of the orange into the square like this. There, now the total orange area is 2 times a of 1 plus 1/2. But now remember the power formula. 2 times a of stuff equals a of stuff squared. And what's stuff squared in this case? Well, 1 plus 1/2 squared, that's 2.25. What does that mean? Well, together the orange bits don't fill the unit square, and so 2.25 is still less than the special value we're looking for. But we've definitely made some progress, right? We now know that the special value is between 2.25 and 3. What's next? Can you guess? Well, instead of 1 plus 1/2, we're now going to go with 1 plus 1/3. Then we can snugly fit 3 copies of the orange into the unit square. And in the formula, all 2's turn into 3's. Evaluate 1 plus 1/3 to the power of 3. That's 2.37 and a bit. Progress again. Neat. What comes after 3? Well, 4 of course, then 5, 6, 7 and so on. And hopefully we'll get closer and closer to our special value. Let me just show you what things look like for 9. There. As you can see, most of the unit square is filled at this point, and it is clear that as we go 10, 11, 12 to infinity, we'll completely fill the square. And so what's that special number that we're going for here? Well, after calculating 1 plus 1 divided by n to the power of n, for some really large n, we find that the special number is approximately 2.71828. And a lot of you will recognize this number. It's a super famous number, e, the base of the natural logarithm. Of course, for those of you who know some calculus, bells will have been ringing for quite a while now, right? Up there, that's how e is commonly defined in terms of that crazy limit. And on closer inspection, our area function really turns out to be the natural logarithm, the logarithm to the base e. And all you calculus demons will know that the relationship between 1 over x and the area function is expressed in terms of this basic integral. One natural question, pun intended, natural. Apart from the natural logarithm, what about all the other logarithms? Where are they hiding? The answer to this natural question highlights another must-know property of our anti-shapeshifter. So let's also quickly chase down those other logarithms and then finish off with some really crazy stuff like hyperbolic rotations and hyperbolic functions that naturally fit in with what we've been talking about today. Okay, so where are all those other logarithms hiding? Well, remember, it all started with the 1 over x anti-shapeshifter over there. What was the first thing we did? We first checkerboarded and then squished by a factor of 2. Let's do that again, but this time without the checkerboarding. Here we go. Squish. That somehow didn't look right, did it? But what exactly seemed off here? Well, let's watch the squishing down action one more time. Squish. Although I definitely squished down, that's not what it looked like, right? It looked like I was contracting the whole shape uniformly towards the origin, the bottom left corner of the shape. There again. And that's it. That's that other remarkable property of our anti-shapeshifter. As far as the overall shape is concerned, squishing down by a factor of 2 is the same as overall scaling down by a factor of, well, what? As you can easily check, the factor is √2. And then stretching horizontally by a factor of 2 is the same as overall scaling up, again, by the same factor of √2. Aha! So what this means for our shapeshifter is that stretching is the reverse of squishing. Nice! Again, easy to check with just one line of algebra. What this also means is that the intermediate shapes we get at the end of squishing are just scaled versions of our original shapeshifter. But since squishing and stretching just moves us between these scaled shapes, it's also clear that these scaled shapes are themselves anti-shapeshifters, right? Very interesting. That means that we could have started with any of these anti-shapeshifters and derived things in exactly the same way as we just did. And that works all the way up to the point of determining the base. For example, let's have another look at the anti-shapeshifter that arises when we squish by a factor of 2. Factor 2 squishing means that our new area function is just what? Well, 1/2 times the natural logarithm. And now, since this function is a logarithm itself, we can find its base as before. The base is the number x for which this function takes on the value 1. And so solving for x, we get this. So algebra autopilot here. And so our anti-shapeshifter corresponds to the logarithm to the base e squared. And in general, the different scaled shapes correspond to the different logarithms. Great stuff, don't you think? And in fact, following the path that we've checked today, it's possible to quickly define and create all the incredibly important number e and natural logarithm related mathematics from scratch, right? Just to really drive home this very important message, let me do a quick recap. Let's pretend we don't know any e-related maths. Start with our 1 over x anti-shapeshifter, show that its area is infinite, show that the area function satisfies the product, quotient and power rules. Now remember, we are pretending that we don't know logarithms yet. We are trying to define all things logarithm and e from scratch. And so at this point, we give the area function a name. We call it the natural logarithm, which is usually written ln of x, which is short for the Latin logarithmus naturalis. Now we find a special number that makes the natural logarithm 1 and call it e. We define e to the power of x to be the inverse function of the natural logarithm. Okay, and maybe also introduce all the other logarithms and exponential functions at this point. Now, from the way we define the natural logarithm, it's clear that we have this identity. From this it follows, give or take the fundamental theorem of calculus, that the derivative of the natural logarithm is 1 over x, and then also that the derivative of e to the power of x is e to the power of x. At which point we've got pretty much all the basic super important e-related mathematics under control. Well, I hope you all agree with me that this visual approach is super slick. And there is a lot of other beautiful e-related stuff lurking just around the corner. In regular calculus courses, this extra material is often covered badly because it's hard to motivate within the standard framework of introducing e-related mathematics. And so, let me finish off by also chasing down some more of these value-adding e-related beauties. I've arranged for all those wedges over there to have the same area. Okay, now any squish and stretch combo will transform all of these wedges into other wedges of exactly the same area, right? If we do this continuously, we get this. So at all times, all these wedges have the same area. Does this remind you of something? No? How about a circle turning? There, all those circle wedges also have the same area at all times. Well, obviously, very similar, right? Now, the observation that the graph of 1 over x exhibits circle-like behavior inspired the 18th century mathematicians Vincenzo Riccati and Johann Heinrich Lambert to investigate hyperbolic counterparts of the trigonometric functions. And so, let me finish off by showing you a pretty natural anti-shapeshifter powered way to go from the familiar trigonometric functions sine and cosine to their hyperbolic counterparts, hyperbolic sine and hyperbolic cosine. Okay, for the trigonometric functions, also called the circular functions, we start out with the unit circle and an angle alpha. There. Then the sine and cosine of this angle are these lengths. In calculus, the angle is usually captured by the length of this arc. Of course, that length is just the angle in radians. Now, expressing an angle by the length of the sector's arc, that's an interesting idea in itself. But you're all familiar with that, right? But what you may not be familiar with is the idea of expressing the angle in terms of the sector's area. When you think about that for a moment, you'll see that this is just as natural as going via the arc lengths, right? Different angles correspond to different areas, and so we can also express angles in terms of areas. What's also nice is that there is a simple visual connection between that arc angle and the area angle, and here it is. Scale the circle and everything attached to it by the square root of 2 there. Everything got times by root 2, and the circle now touches the hyperbola at a point. Now you can easily check that the value of the area of the scaled sector is equal to the original arc length. Again, the green area of this expanded sector is equal to the angle in radians, the length of the original arc. Now, with the circle and the hyperbola touching, we're almost where we want to be. Okay, the point where the two curves touch, that's the super special point of the 1 over x hyperbola. And so what we want to do now is to align everything inside with this point. And we do this by rotating everything through 45 degrees like this. Okay. Now I extend the circular sector to a hyperbolic sector and define the two hyperbolic trigonometric functions as lengths, just like the trig functions were defined in the circle. Well, the names of these functions are obvious, just the trig names with an added h. But now, how should we say these hyperbolic functions? Well, spelling it out, how about cosh and sin he? Cosh is pretty good, but sin he doesn't sound that great, does it? And so the hyperbolic sine function is often called shine. We cheat by putting the h with the s. Shine, I like it. Anyway, names aside, all pretty natural, right? Again, here the angle alpha is the area of the green hyperbolic sector. And now, pretty much any property of sine or cosine has a counterpart for these hyperbolic trigonometric functions. For example, take Euler's formula. The hyperbolic counterpart of Euler's formula is super pretty. Just get rid of the i's. Whoa! The exponential function is just the sum of cosh and shine. And so the exponential function itself also has a nice geometrical interpretation in terms of the sum of the two lengths in our diagram. Super pretty. I'll give an animated proof of this fact at the end of the video, something to really look forward to, I promise. Actually, for all this to make sense, we have to declare that when the angle flips to the other side, both the angle and shine are to be interpreted as negative numbers. But that doesn't come as a surprise, right? After all, we do the same sort of thing with sine and cosine. Anyway, with this convention in place, let's replace alpha by minus alpha. On the right side, things simplify, since cosh minus alpha equals cosh alpha, and shine minus alpha is equal to minus shine alpha, we get this second pretty identity up there. Now, if we add the two identities, have a look, the plus and minus shines on the right cancel, and we get the famous way of expressing cosh in terms of the exponential function. On the other hand, when we subtract the two equations, we can solve for shine and get this. A minus instead of a plus on the left, very nice. And also, with what I've shown you, it's now straightforward to prove the hyperbolic counterparts of all the other basic trigonometric identities, like for example, the counterpart of the famous sine squared plus cosine squared equals 1 identity, this one here. Great stuff, right? And why is all this important? Well, hyperbolic functions pop up all over the place in physics and engineering when it comes to describing natural phenomena. For example, the graph of cosh describes the shape of hanging chains and cables. And those squish and stretch hyperbolic rotations lead a second life as Lorentz transformations in the theory of special relativity. To see this in action, check out the super nice Minute Physics video that features that mechanical Lorentz transformation simulator over there. A couple more hours worth of amazing stuff to talk about, but let's stop here for today. I hope you enjoyed this mathology video. Please let me know what worked and what did not work for you, and ask all your questions in the comments. Until next time. you.